Well, good afternoon, and thanks so much for having me. I was thrilled to get the email in my inbox, so the feeling is mutual. So I get to tell you today about Snorkel, which is an open source project that I've been involved with for about 4 years at Stanford. And first I'll lay some of the groundwork for what problem is that we're trying to solve here. You can think of machine learning applications as having three components. There's a model, there's data, and there's hardware. And thanks in part to fantastic libraries like Hugging Face's PyTorch transformers, it is becoming increasingly easy for everyone to have access to state-of-the-art models with literally just a few lines of code. Pip install the library and then import BERT or import GPT-2 or whatever the latest, greatest model is. This is now super accessible. Same thing on the hardware side. Thanks to cloud computing and various nice frameworks, again, with just a few lines of code, you can have access to the latest, greatest GPU or TPU or whatever PU comes next. And if you need something that's larger, again, change your flag type, and now you are also running on state-of-the-art hardware. So all of this is just to say that models and hardware are increasingly commodity, and you can have access to really good stuff here with not too much effort. What's not, though, in that category is training data. Training data for real-world applications, not benchmarks, but the one-off application that a doctor or a data analyst wants to spin up. This is where they tend to get stuck or spend the most amount of time. And so that's where my research is focused for the past number of years. How can we get enough training data for new applications? And part of the reason why training data is such a bottleneck is because the current approach, most of the time, is manual labeling. You or a warehouse of people somewhere will spend hours, days, weeks, sometimes months labeling individual examples as true and false and true, one at a time, every individual example being seen by a human. And this has a number of obvious drawbacks. One of these is that it's very slow, because your millionth example will take just as long to label as your first example. It's linear in scale, and so it never really gets easier. You never get the economies of scale benefits. It's also expensive because, again, this is humans doing the labeling. So at best, you're paying minimum wage. At worst, you're paying for a doctor or an expert, someone who costs maybe hundreds of dollars an hour. And then it's also very static. For a benchmark task where you have a single data set and a single score you're trying to get, you don't often have changing needs because that would mess with the benchmark. But when you're in the real world, needs change all the time. You may have had a 2-class problem that's now a 3-class problem. And what do you do with all of your old labels? You can't use them anymore because you don't know how they map to your new setting. Or even if your schema stays the same, it's possible that your data distribution changes over time as new topics are being discussed, as new features begin to occur. So the fact that it's static is basically just saying you'll need to relabel often, which again is slow and expensive. So the alternative approach that I propose, and which you may have gathered from the title of my talk, is that instead of manual labeling, I recommend for many use cases, not all, but for many, that you do programmatic labeling. And the question here is, what if instead of having to see each individual example myself, what if we could encode our domain expertise in programs and have these programs label for us to create the large training sets that our deep learning models need? To compare then this to manual labeling, it's fast. There is some startup cost to making these programs, but once you have them, executing them is almost instantaneous. This is now seconds or minutes, not months of time spent labeling. It's also cheap because computers work for far less than humans do. And it's now dynamic because if you need to make an update to your schema, to your data, you can modify a few lines of code and push re-execute and have your new labeled training set again, almost instantaneously. So a lot of benefits if we can make this work, and that's what we've aimed to do with Snorkel. So I'll talk now a little bit about Snorkel, introduce you first on the background. This began as an open source project at Stanford, and it's seen a lot of different publications during the time that I've been there. Some of these have been on the core machine learning algorithms that are running behind the scenes. Some of it are in natural language processing applications, which I've been a part of most. There are systems papers where we've talked about how you make this work at scale, how you approach this problem systematically, and then some other applications papers with a couple in Nature Communications this year, for example. But it's not just an academic problem. We've also had a lot of success applying this with our collaborators to problems in industry and science and government. So these are the logos of some of the companies that we've worked with. With a handful of them, we've actually been able to co-publish papers like Google and Intel. But from all of them, we've been able to get invaluable feedback on how to make this process very practical and in a way that works outside the ivory tower of academia. We just less than a month ago put up a new website, snorkel.org, where you can find more details on anything that I talk about today. We've got links there to all the papers that I referenced, as well as tutorials and other descriptions that explain more about Snorkel. So how does it work? The Snorkel pipeline begins with the domain expert not labeling individual examples, but instead writing these labeling functions, these simple programs that are going to do the labeling for you based on, though, your intuitions that you have encoded in them. And a labeling function is simply a black box function. We assume nothing about what's inside, what type of resources you're using, what type of logic you can support. All that matters is that this is a function that takes in a data point and outputs a label or abstains. And we fully expect that these labeling functions will not label all of your data and will not necessarily be as accurate as a human. And that's absolutely okay. We're going to get enough of these that we can combine them and take out the best parts from each, and then ultimately end up with a fairly clean training set at the end of the day. So I'll walk through an example now of a labeling function that you might write. Assume that we're trying to classify emails as spam or not spam. Looking at this as a human, we recognize this is most likely spam. And one of the things that might have tipped us off is this phrase, need money. So we could write a labeling function that says, if in an email I see the word or the regular expression need money, go ahead and label that as spam. And in this case, the label that it outputs is correct. Fantastic. But there might be other emails where this isn't true, like this one from my grandma asking if I need money. Applying this same labeling function gives us the spam label, which in this case is incorrect. But again, we're okay with that. We expect some amount of noise, and you'll see how we're able to still denoise the labeling functions when we combine them to get better outputs. Before I show you how we actually do that combining process, though, I wanted to just emphasize labeling functions can be more than just keyword matching. That's an easy one for me to show and an easy one to demonstrate or imagine, but really there's a lot of room for creativity here. These are mostly focused on the NLP setting, but just to give you a sense of the types of things you can do, if you have a database, say of known spammers, you can do lookups there. This is what people sometimes call distant supervision in the field. You can use heuristics, like looking for a certain number of spelling errors or the length of the email. If you have an existing system that you're using, whether it's machine learning based or not, you can wrap up that legacy system in a labeling function and therefore keep all of the prior work that you've already done on this problem, but hopefully improve on it further when you add in all of these other sources. So I guess this is just to emphasize that, especially as we've worked on all these different collaborations with different partners, labeling functions take all different types of forms, but there often is more signal that you can take advantage of than you might think at first. So first, the user writes these labeling functions. The next step now is to combine them. And we do this with the class inside Snorkel that we call the label model. And it's important to note that this label model does not use any labeled data. We're able to, in an unsupervised way, come to identify which of these labeling functions are more trustworthy than others. I'm not going to go into the math here since that's not the focus of the talk today, though on the website you can find those papers. But the basic intuition that we're going to use is that on average, our labeling functions are non-adversarial. That on average, they're better than a random guess. And so the more frequently that a labeling function is disagreeing with others, the less likely we should be trusting it. And this harkens back to a lot of classic results on mixtures of experts or crowdsourcing and how you combine lots of noisy sources and learn when to trust them. So user writes labeling functions. These are denoised, we say, or combined to produce a single probabilistic label per example. And then the next step is going to be now training a classifier with that generated set of labels. And if you're looking at this, a common question we get and that you may have right now is, if my label model already takes in examples and outputs a confidence-weighted label, why don't I just threshold that and make that my classifier? And there are a number of good reasons for that. It looks like I did one thing out of turn. This is just emphasizing that that model is not necessarily part of Snorkel. We recommend you keep and use whatever model makes the most sense for your problem, potentially using one of the fantastic libraries out there that provide things like the BERT or the ResNet or whatever makes sense for your problem. So now the question I just asked, why don't I just use my label model directly? There's a number of good reasons here. I'll show you two. One of them is that we get improved generalization. So when you write these labeling functions, because they're heuristics, it's nice that they're interpretable and direct, but they often don't catch the long tail of minor variations in your data. They are, after all, just lightweight heuristics. So, for example, here on the left, we can see that some percentage of our data set may not have any labels on it at all from our labeling functions. And if we tried to use our label model as our classifier directly, it would know nothing about those examples and couldn't make a relevant prediction. But it's pretty intuitive to us that if I was to take just the points that have color in them, some number of labels from our labeling functions, and then train a classifier on that, we could learn the decision boundary, especially in the simple case, and thereby predict correctly on all of these white points, because it's able to generalize using other features. So to give a concrete example of this, in one of our papers, we were trying to identify mentions of chemicals causing diseases. And so some of the keywords, the clues that we were looking for, based on our labeling functions, was the presence of a word like treat or cause or induce. And all this makes sense to us as a human. But then after we made a training set using these labeling functions based on these types of rules, we found that our model came to trust other n-grams that we hadn't ever specified, like could produce or support diagnosis of. So that is to say, it was able to learn and how to take advantage of other features that are correlated with the ones that we identified, but not explicitly identified by a human at all. So you're able to really sort of get this boost for free, about the same precision, but an improvement in recall because of this ability to generalize. A second reason why we like this, the setup that I showed, is that we can now take advantage of unlabeled data with very little extra work. So this is a figure from one of our papers where we had a certain set of labeling functions, about a dozen or so, and we didn't change those at all. We simply dumped in more raw unlabeled data. And so more unlabeled data in means we get a larger training set out, which again requires no extra human effort because labeling is now programmatic. And with a larger training set, our model got a higher score. So it feels kind of like magic when you're doing it, that you can just dump in more raw content and get a better score, but it makes intuitive sense because we are, at the end of the day, getting a larger training set to then feed our model with. So that's how it works. How well does it work now? Let me walk through a couple of the places where we've used this publicly. So this is a figure from the paper that we wrote with Google about their internal deployment of Snorkel called Snorkel Drybell. And as you might imagine, Snorkel has a lot of different internal resources that they can take advantage of. They had an existing system for tackling this problem. They had heuristics, a knowledge graph, custom classifiers, lots of different things that they could wrap up into labeling functions and now bring all of them to bear on this problem. And we don't specify in the paper what exactly the problem was for confidentiality reasons, but trust that it was a highly engineered one that they had great interest in doing well at. But it was interesting that even with all the effort they had spent, when they then took this approach of combining multiple different weak supervision sources that individually weren't good enough on their own to give them the quality they wanted, but if combined, do provide a lift, they were able to see double-digit improvements on some of their applications. Another application that we worked on that was a lot of fun was with Stanford Medicine. So here we were trying to classify x-rays of chests as normal or abnormal, perhaps as a triage step for whether this should get a second opinion by a doctor or how it should be prioritized. And these doctors spent some number of person months labeling chest x-rays and trained a classifier with it, and this is the curve that they got. And we want to be up there, in the upper left. It stole my thunder with the accidental click, but when they went and labeled 10 times as much data, this is additional months up to the point now of being person years of labeling, they were able to get an even better score. But we then tried to see what if we tackled this problem or one similar to it with Snorkel. And this was an interesting problem in part because labeling functions were a lot easier to write over text than over pixels. And so these doctors had, with each of these x-rays, an associated report where the doctor who looked at it had written notes. So when we worked with the doctors to make this Snorkel application, they wrote labeling functions over the text reports. And we combined those and got probabilistic labels, which we then transferred to the corresponding X-ray images. And with that, we trained now an image model. So once this model's trained, in the future, new X-rays don't need an associated report. It just accepts an image in and makes a prediction. But after writing just 20 labeling functions, which took about 1 day of us sitting with them and helping them know how to how to encode these things, we achieved within 1 point accuracy using Snorkel. And now this is much more dynamic, so that if they decide they want to have a third class, like abnormal or abnormal and acute, like an emergency, that's something they can add by modifying some of these lines of code and then simply re-executing. So there's 2 applications we've worked on. Now I'm going to walk through how you might go about using it for one of your own problems. On the website, we've got a bunch of different tutorials. I'm going to go through some of the high-level points of one of them here, but you can do the full thing there. And in addition to being on the web page, we also, for each one, have the associated Jupyter notebook, where you could go through and actually modify cells and play around yourself if you have interest. So the task that we worked on for this problem was looking at YouTube comments, comments that are posted on a YouTube video, and classifying them as spam or not spam, which I'll call ham for abbreviation. And spam comments are not necessarily dumb comments, just ones that aren't related to the video. So here's some examples of spam that we saw in the data set. It's often people asking for you to come subscribe to their channel or look at their video, something not related to the current video that we're on. And ham comments are things more commenting on, I love this song, I love what happens at 346, this is so cute, things like that. So step 1 of the Snorkel pipeline is to write these labeling functions. So one thing we might do, as I mentioned before, is to look for keywords. In this case, check out. We see this, people saying, check out my video, check out my channel, not talking about the current video. So we'll go ahead and write a labeling function. We mark it with this little decorator, and then it's just a simple Python function. And we'll say, mark it as spam if I see the words checkout in the text, otherwise abstain. Another labeling function we could write is a heuristic. We may notice that, in general, the ham comments tend to be shorter than the spam ones, because the spam ones may include a link to their channel or something like that. So we'll write, again, another labeling function that says, if the number of words in the comment is less than 5, then go ahead and call it ham, otherwise abstain. And as you might expect, this isn't perfect, but it ends up being one more source of signal that we can take advantage of. And I'll show you one more type of labeling function that we wrote. I did a Google search for a sentiment classifier and found one in a library called TextBlob. So TextBlob is a pre-trained model, or it includes a number of things, but one of these is a sentiment classifier. And when I applied this to our data set, I found that there's a different distribution between the ham and the spam comments. And so even though sentiment analysis is a different task than spam classification, there's some similarity there that we can take advantage of as a labeling function. So we wrote one that said, if the polarity score is greater than 0.9, go ahead and call it spam, or ham, otherwise call it spam, just because that's one area where we saw that there was a significant difference in the distribution. So gathering 10 of these, which we I think wrote in about 90 minutes or something. A bunch of them are keyword-based. We have a regular expression, 2 of the text blob ones, things like this. We have now a set of labeling functions that we can combine and work with. And a couple things to note here. One is that none of these labeling functions on their own have enough coverage to label our entire data set. A lot of them are in the teens. Looks like we have one around 40%, but obviously we're going to need to combine multiple of these if we want to be able to cover our entire data set or our entire test set. The other thing to notice here is I pulled out a small sample of 200 labeled examples just to give us an idea of the estimated accuracy of these labeling functions. And some of them are quite good, like asking people to subscribe, but a lot of them still are lower than we would like. If we're trying to train a classifier here that's 90 or 95% accurate, it's pretty neat that we can still use sources that are as low accuracy as 66%, because there's a little signal there that, again, if we combine with others and learn how to denoise, will still provide some value to us. So we've got our 10 labeling functions, and we're going to apply them now to our training set. And our training set in this case is stored in a pandas data frame, so we use our pandas LF applier, get back out of it the L matrix, and that's just n by m, so number of data points by number of labeling functions. And that's what we're going to give as input to our label model. And as I mentioned, the output of the label model is probabilistic labels. So this is the output label distribution that we ended up getting. You can see that there are some examples that we're very confident are spammy, and there are some that we're pretty confident are ham, and then there's a whole bunch here in the middle, around 0.5, that we're really not sure about. And this is reflecting the fact that our set of labeling functions does not have perfect coverage. It's heuristics, it's not complete, but again, we can get past this by training now a discriminative classifier with a larger feature set. So step 3, we're going to take that set of labels that we've generated, the probabilistic labels, and train a simple classifier. In this case, we kept it very simple and just used a bag of n-grams, a bag of words essentially, and a logistic regression model using Keras. It took maybe a dozen lines to define and run, and then we see how we do. So looking at results, if we had taken our labeling functions and just combined them in a majority vote style, if you have more votes for spam than ham, call you spam, and vice versa, we get 84%. And this is pretty cool because, again, a lot of our labeling functions had accuracy lower than this, but we're combining them, and so we can take advantage. If we use our label model, we get an extra 2.5 points almost for free. It runs super fast, and now by just learning in an unsupervised way which ones to trust more, we do better. But then the biggest jump comes when we train a classifier with this, and we now have a classifier that's 94.4% accurate overall on our test set. And that came from, again, these weak, dirty, somewhat ad hoc labeling functions that we were able to come up with. So what happens next? How could you guys find out more about this or use it yourself? Well, in this talk, I talked about using Snorkel to label training data, writing labeling functions. There are 2 other operations that we support natively in Snorkel that you can find out more about on the web page. One of those came up today in the panel, and that's data augmentation. This is doing things to transform your data points into new versions of them, either modified or new copies, that will teach your model to learn certain invariances, like a cat looking left should be treated the same as a cat looking right. They're both cats. And doing stuff like this, you can often end up with multiple times larger training sets that are still effective for your model. The other piece that we have is using what we call slicing functions. And with this, you can identify certain subsets of your data that are particularly important to you that you want to monitor performance on as you train a model, as you supervise your model, or we even provide a slice-aware model that you can use to, in an attention-based way, improve on specific subsets of your data without dropping overall quality. So for more on those, check out the website, and you can find the associated papers and work there, as well as some tutorials. Last, Snorkel, as I mentioned, is open source project, ongoing work. The website I've mentioned a number of times now has content. You can also contribute to the repository. We get feature requests, pull requests, even better, and that's active and a lot of fun. There are tutorials, and we're always adding more. There are 7 or 8 right now, and you can use that to pattern match on your own type of problem that you're interested in. There's a forum for discussing high-level questions, the documentation, and then on Twitter, we'll announce whenever there's a new tutorial or another paper or different things like that. So with that, thank you so much, and happy to answer any questions.
Okay, thank you, Braden. So we have 3 questions. The first one is how labeling functions can be reviewed, and how to avoid biases in label functions. Yeah,
that's a great question. So bias, I think, in machine learning is a topic that continues to grow in interest, and rightfully so. It's a huge deal ethically and practically. And so it's something we thought about as well. And there's a great whole field of work on how to detect bias in our machine learning models, and that is something that's orthogonal to necessarily how you generated the data that trained the model. But one thing that's nice about this process now, when your labels for your training set came from a programmatic process rather than humans, is that they're inspectable. And so if you train a model and then you discover that it's biased, that it maybe has a gender bias, you can go back and actually turn on or turn off individual labeling functions or evaluate their individual results and see where this bias is coming from. So in that way, I would say gives you a little more insight actually into the source of your labels, rather than if it comes from humans, from crowd workers, it's hard to say what they were relying on when they provided their labels. In terms of how to review them, there's lots of options. In general, the answer is more labeling functions is better than finely tuned labeling functions. So we often focus mostly on quantity and rely on the model to denoise them appropriately. But like any other thing, you can get a small labeled development set, like the 200 examples or so that I showed, and as you're developing, check out performance and tweak accordingly.
Okay, thank you. What are the limitations, do's and don'ts?
Yeah. Limitations. I mean, a few things that we kind of count on having with Snorkel. One is that you have a model that you want to train. So model architecture is something that you're on your own for, I guess. But fortunately, there are model zoos and great libraries and things already out there. Some domains are more difficult to write labeling functions over. I showed you an example over images where we actually ended up supervising the images via the corresponding text. We have some other work where we actually pre-process images to provide a bunch of primitives to refer to. So we'll take off-the-shelf like segmenters, chunkers, object detectors, and apply them. So then you can say things like, if the image has a picture of a cat close to a cup, then do whatever. And that uses the cat and cup tags that were generated by that other model you already ran. So sometimes you need to get creative there because, for example, it's hard to say, write a labeling function over particular pixel values. But there often are ways around it, either with a cross-modal example like we showed, or by getting these primitives from other types of models.
Okay, and does Snorkel work with sequence labeling?
Yes, it can. In its simplest form, it's a classification problem. But we have just recently published, it's more on the research side. It's not, I don't think it's baked in fully into the open source code yet, but we have demonstrated how you would do it, how you would label examples that have temporal dependencies like a sequence. So that one I'd say is still more on the edge, but certainly doable.
Okay, thank you. And is there a way to use Snorkel for object detection task?
Yeah, so I guess this is somewhat related to the past question. Snorkel is, in its current form, largely a classification tool. And so object detection, if you can phrase it or format it as a classification problem, then it would work. So one way you might do that is have some process of generating candidates to classify, and then have train Snorkel to classify these candidates as different objects. If you're training a car classifier, for example, then you could take any of a number of available off-the-shelf types of taggers that maybe have high recall but lower precision than you need to generate a pool that you can then classify as, yes, that is a car, no, that's actually a bike, things like that. And that's actually, Snorkel began as an information extraction tool, which is similar to that, where you generate lots of potential things that could be the thing you're looking for, and then you identify which of those are the true positives and which one you can ignore. So that's how you would phrase a problem like that.
Okay, thank you. Okay, I see a question. I see you.
And this question is, can you back to slides when you show results? I saw in your tutorial that without generating notification you had 92%. How you combine them and know what to train in which labels you train? I don't understand what it means labels generated. It's everything which was generated by your label model, or you something combine your initial labeling stuff.
Yeah, it's a good question. So, I mean, when we've got some number of labeled examples already, the question is, how do I know whether to use those or to generate new stuff? And it's somewhat problem dependent. I mean, if you already have a very large labeled training set, in general, go ahead and use that. You've got ground truth labels and lots of them, go for it. Though, I mean, we are finding, for example, with some of these, in the whole transfer learning world, that even when you have labeled data, you can often still do even better by making a large related data set that's noisier and pre-train on that first before fine-tuning. So it'll depend on the exact quantities and the difficulty of the task, and there often are creative ways to combine gold labels that you already have, whether that's as a fine-tuning piece or make that another labeling function and say, the labeling function is, if I have a label, use that. And then that'll end up being a very high precision LF that will get trusted.
So firstly, we are so for this task, you don't have any train labels, yes? And you only have dev that set. Mm-hmm. And for example, general task, you recommend to label with this for functions your unlabeled data set and operate on it, and then fine-tune on your labeled data. Something like this.
Yep, that's entirely an option. So that is the typical, I'd say, workflow for starting from truly ground zero is first label a test set so that you can, at the end of the day, see how good it will do. And then often there is some small dev set that you'll label for, and this is like very small, way smaller than a training set, like a couple hundred, just to sort of guide you as you make labeling functions and give you ideas for, am I way off base here, or is this a relevant signal?
And could you give some insights about your superglue approaches, how to increase the score, how you did it in your research?
Yeah, absolutely. Yeah, so we were the first submission actually on the superglue task and got a new top score there. They've since added a couple of new tasks and we haven't resubmitted, so there's an asterisk by our score down at the bottom because it's missing some pieces, and we may revisit that. But the way that we were able to beat, they started with a very strong baseline of BERT++, which was a BERT pre-trained model fine-tuned on MNLI, one of the tasks that's proven to be a good intermediate task, and then finally fine-tuned again on each of the individual tasks. So this was one of the fairly high results on glue that then applied over to superglue. So what we added on top of that was partly some data transformations, like modifying one of the tasks. We found a way to adjust the format the data was in that made it easier for the model to do better on. But the main contribution we had in our superglue submission was taking advantage of these slicing functions. So we used a multitask model, and we had these, again, heuristic functions identifying subsets of the data that had, basically just chunks in the data that had some similar properties to each other. And then our multitask model ends up learning to specialize. A different head will specialize on each of those slices. So then at inference time, when it sees a new example, it's able to estimate how confident am I that you are a member of this slice? And if so, I'll use more of the expert head's representation as I make my prediction. So it's a little more involved, but ended up working out really well in a way that, again, was driven by these heuristically identifying and working with your data to inform and improve your model. There's a technical report on that slicing work that's coming out this weekend, if all goes according to plan. And you can find that on the website, or we'll tweet about it when we release that.
Hey, Braden. Thanks for the great description. I have two somewhat different questions, but both are related to the topic of methodology and model validation with weak supervision. So the first question is the output of the labeling model probabilistic? And if so, would it make sense to transform the machine learning problem into a weighted machine learning problem where we have sample weights assigned to each data point such that if the labeling model isn't certain about the class label, then it would be okay if we misclassify it? So would it make sense to apply sample weights if?
Yeah, your intuition is exactly right there. We do, in fact, do essentially that. So with these confidence-weighted labels, if you have a model that only accepts integer labels, you can just threshold them and use the rounded weights. But wherever possible, we use what we call like a noise-aware loss. Basically, you use a target distribution, sort of like distillation, actually, where you say, rather than, essentially just that. Use a float label and use sort of a average of the cross-entropy loss over the classes that you have. So the result is that if we have a marginal probability of 0.5, then it will have the same loss whether it predicts 1 or 0, so it doesn't try too hard to get that right, compared to something that we're pretty confident about. So that's exactly what you can do and what we do usually in practice. Yep,
thanks. And the second question is, how do we combine this approach with train dev test splits? So the intuition is once we start adding more and more labeling function, at some point we'll start either leaking the test data distribution into our feature extractors or labeling functions, or we start overtuning to the training set. So how do we validate that adding more labeling function still allow our model to be generalizable? So yeah. Do you suggest some particular validation setup for checking when the optimal condition is reached?
Yeah, great question again. So we, for one part of the answer is we use the same generally accepted good practice of make a test set at the beginning and never look at it until the very end, or extremely rare evaluations, but never do error analysis or anything like that. If you are using a small labeled dev set to give you ideas for your labeling functions, then you are susceptible to overfitting on it, like you mentioned. And there are different ways of dealing with that. I mean, one thing worth noting is we never actually rely on the labels of that dev set like to train on. And so at worst, they'll make you maybe think that your labeling functions are more accurate than they actually are. But then they're going to be applied to your training set, which is a separate set. And again, we're kind of prepared to deal with some amount of noise. So in that way, it's nice that we're not going to use double use, I guess, any label that we already have. So that protects us somewhat. One other thing that you can do, though, and that we've done in some papers, is measure the diversity of our set of LFs, make sure that we're relying on different attributes, labeling different classes, that we're not don't have labeling functions that are too similar, or if they are similar, that we include that in our label model. There are ways of specifying known dependencies between labeling functions so that they're not double counted. And so you can deal with it that way as well.
Okay, thank you. We can do one more question. Anyone? No questions? Okay, then thank you, Braden, so much. Thank you, guys.